Hello everyone, welcome to Mindspan Education. Last video we looked at the law of iterated expectation or law of total expectation. Both are the same thing. And also we looked at the law of total variance. In this video we are going to look at few of the applications where you will find we will be using these two laws, that is the law of total expectation and law of the total variance. And we will see that how powerful these two are. In order to do what we are going to do, so there are lot of scenario where you will have a random variable that will be the sum of the other random variable, right? So might be these are the distribution that are simpler distribution, and now maybe further on you will be exploring or you will be analyzing a distribution that is the sum of this distribution, and you will be doing some operations on those, that like finding the expectation of this random variable y and finding the variance of this random variable y, that is the sum of these distribution, right? And here the one more twist is there, that we have already seen if we have a fixed number of distribution, right? If we have the fixed number of distribution, then if we try to find the expectation of this random variable y, that would be the expectation of this x1 plus x2, and if we have some n number of such distribution, then using the linearity we can have the total expectation of this random variable y, right? And if these random variables are independent, then we can also find the variance of this random variable y. And if these distribution are fixed, the number of distribution are fixed, and if these are independent, then we can simply say that this will be equal to the sum of the individual variance, right? The twist is here that the sum or the number of distribution that you have is also a random quantity or is also a random variable, right? So this n is a random variable. Now we are trying to find the expectation and the variance of this random variable, that is the sum of random numbers of independent random variables. So let me first of all describe you. So I think as of now it is clear that how many terms are how many sum of these will be there is again a random quantity that depends upon the value of this n, right? So this n is a random variable itself. Let's take an example and let's try to understand. Before I proceed, let me give you a update that recently we have launched our GATE DA 2026 test series. Currently it is available on 25% discount, and this discount will be valid till 31st of July, right? So you will be able to enroll this test series at 999, and after 31st of July the test series will be available at its original price, that is 1332. All the details will be available on mindspaneducation.com. You can visit this page and you will have all the infos regarding the test series, that how many number of tests will be there, what's the schedule of the test, and so all the details will be available here, right? And still if you have any question, you can write us email, you can contact us directly, you can call us. All right, now let's proceed with our topic. So now let's take an example. Let's suppose that you are visiting some stores, right? And the number of stores that you visit is a random quantity, and let's suppose that this we denote this with n. So n is a random variable which is defined as the number of stores you visited, right? So you will visited maybe 1 store, maybe 2 store, maybe 3 store, right? So n can take the value that is non-negative or any integer, right? And this n will be a random variable. Now on each store you are spending some money, right? And we are going to denote this with random variable xi. So this is again a random variable, that the amount of money you spent on a particular store, that on the ith store is a random variable that we are denoting as a xi, or we are defining it as a xi, right? And the distribution, so you are going to visit any random number of stores that is captured within this number, that is a random variable n, right? So you visit first store, right, and you spend this x1 amount of money, and this is again random variable. And what we are saying about this random variable is, so we will have multiple such random variable. X2 will be again a random variable, x3 will be again a random variable. So this is the amount of money you spend on second store, this is the amount of money you spend on the third store. And what we are saying is that all these random variables have a common distribution. Maybe it will have a normal distribution, or maybe it will have a uniform distribution. So what I am trying to say, all these x1, x2, x3 have a identical distribution, right? And we are taking all these x1, x2, x3 from this identical distribution, right? So that is the second thing. And the third thing is that these random variables, that is x1, x2, x3 and x4, all these are independent to each other. So overall I can say these random variable xi, so this random variable xi is identical, independent and identically distributed. And you will see that we have the short notation for that. It means that independent, identically distributed. So this random variable xi is taken from the common distribution, and all these xi are independent, identically distributed, that is IID. And let's suppose that each of xi, or each of random variable, so since we are getting this random variable from a common distribution, and the expectation of this common distribution, let's say this expected value of x, so we are denoting the expectation of the common distribution. It could be any distribution, right? So the expectation of that is the expected value of x. This is what we have been given in the question or in the information, right? And the third information that we have is that all these random variables, that is x1, x2 or xi, is independent of this random variable n, right? So this random variable n is independent of this random variable xi. Now we have been asked that what will be the expected amount that you will spend. That means we are trying to find the expectation of the sum of these random variable, and we will sum till this big n, and this big n is now again itself a random variable. So we are trying to find the expectation of that, right? I hope the problem statement is very clear, and what we are trying to find, that is also clear, right? So here if you see that how many number of terms will be there in the sum, that depends on the value this random variable, whatever the random variable n will take the value, that number of terms will be there in the summation. Alright, so how we can proceed and find the expected value of total amount that has been spent, right? So what we can do, we can condition on one random variable. We can say that let's suppose if So by conditioning, we will be doing some simplification. So let's suppose if we say that this random variable takes a value that is little n, right? So maybe n is taking the value 5, or maybe n is taking the value 6. So we are just conditioning over this random variable, and given this condition, we are trying to find the expectation of the sum of these random variable, that is x1 till xn, right? And so now we are residing within this universe, right? So we are fixing this capital N, that is a random variable, and it is taking the value that is little n. So we are residing this universe. Within this universe, what will be this sum? So this sum will be from x1 x2 till where random variable capital N will take the value little n, right? Given that n has taken the value little n. So we are trying to find the conditional expectation of that. And we have also given that this random variable n is independent of these xi, right? So happening of this event, or if we have the information about this event, that information about this random variable and takes the value little n, and since these random variable are independent of each other, that means happening of this event should not affect my belief about of happening of that event also. So this conditional expectation would be equal to this unconditional expectation, since these xi and the random variable n is independent of each other, right? And we have also given that each of these random variable that are taken from a common distribution or identical distribution, and the identical distribution has the expected value, that is expectation of x, right? And we are summing such distribution, n number of distribution, and we are trying to find the expectation. So using the linearity, we can directly say it will be n times the expectation of each one, right? So each one has been taken from the identical distribution, and each have the expectation, the expected value of x, and we are having such n terms. So the expected value of these sum will be n times the expectation of x, right? So now we have condition, but we have to find the total expected amount that has been spent, right? So now what we can do, we can make use of the total expectation theorem. So what this total expectation theorem says, that is equal to the conditional expectation. So you have condition that n takes the value little n times the PMF or whatever probability of this random variable, or probability of this scenario, each scenario, right? So we need to weight this conditional expectation with the corresponding probabilities of the scenario, and we need to do this for all the possible values of the scenarios. So this sum will over the n, right? So this is what the conditional expectation, this is what the total expectation, right? And we have already found this expectation, right? So that is, so I think I do not have to like repeat this statement again, right? That how and what we are referring here, and what is this, the total expectation theorem. We had talked about this total expectation theorem multiple times, right? So now let me proceed further, and this can be written as, so we will have this, the PMF of this n will be here, times this we have calculated as n times the expected value of x, and since this term, that the expected value x will be a numeric quantity or constant, we can put out this expectation of x outside the summation, and now let me not use the multiplication sign so that you will be get confused with the x, I think. So let me put the dot here, sum, that is goes over, and if you recognize this, what is this? What is this term? This is nothing but the expectation of n, expectation of random variable n. Right? So we have found the expected amount, the expected amount that is going to spend, that is equal to the expected store that you visit times, sorry, the expected store that you visit times the expected amount that you spend on each store, right? And it is quite intuitive in the case of expectation, right? Alright, and this can be seen, so how we have seen this total using the total expectation, right? And this can be seen also using the iterative expectation. So let me show you that also. So what is iterative expectation or law of the total expectation? It is nothing but just the total expectation, right? So we are trying to find the expectation of this conditional expectation, right? So this is also the total expectation, right? Or we have already seen that the law of iterative expectation is nothing but just the total expectation. We have the abstract way of writing this total expectation theorem as a law of iterated expectation, right? We need to find this random variable, right? So what is this random variable? We are trying to find the expectation of this random variable. So this random variable is nothing but here if you look at, this is the special case where this random variable is taking the value, where n is taking the value little n, right? So this random variable that we are talking about, the expectation of y given n, or this conditional expectation, is a random variable, right? And it can take the value this when n is equals to little n, right? And depending upon the value of n, it will take the different values, right? So overall we have seen this as a random variable, and we are trying to find the expectation of this random variable, right? So if we have to write this thing, this conditional expectation in general, right? So this will be a fixed value, or when n takes the value little n, right? So this will not be a random quantity, this will be a numerical quantity, right? But if we write this for in general, that n times the expected value of x, right? Now depending upon whatever the value n will take, we will have this conditional expectation. So now this thing is a random quantity, so that is equal to this conditional expectation, right? I hope it is making sense, and I am sure that you have already gone through my previous video. So this can be written as n times the expectation of this random variable x. So this quantity will be a constant, right? The expected value of this random variable x will be a constant. We can pull out from this expectation, and now we will have the same thing, that the expectation of this random variable x times the expectation of this random variable y. And what is this thing? So this law of iterated expectation is nothing. So the expectation of the conditional expectation, and if we try to find the expectation of that, we will get the unconditional expectation, that is the expectation of this y, right? The same thing we have seen using the iterated expectation, law of iterated expectation. Alright, I think it was the obvious result, right? That the expected amount of money that will be that you will spend is the product of the expected value or the expected amount that you invest on or that you spend on each store times the expected number or the expected amount of stores that you have visited, right? It was quite straightforward, but still we have carried out the mathematical proof so that you can write it with the confidence. Alright, now if I ask for, so we have done one operation on this random variable y. Let's do another operation. Let's try to find what will be the variance of this random variable y. Can we say that like the expectation? No. You will see that it will have other terms also, right? It is not quite straightforward as the case of the expectation. Let's try to find that one also. So now what we are going to look at is the variance of sum of random number of independent random variable, right? So we are trying to find the variance of this random variable y, and this random variable y is the sum of these random variables, and how many these random variables will be there is itself a random variable, and that is defined by this random variable n. We are trying to find the variance of this random variable y, right? You might have one like if you already have seen that the variance of random variable x1 plus x2 is equals to, if these two random variables are independent, then the variance would be nothing but the sum of these individual variance, right? If we have such n random variables, right, if we have such n terms, like let me x1 plus x2 plus x3 plus let's say x4 plus x5, right, then the variance of this will be the variance of this random variable x1 plus x2 plus variance of x3 plus variance of x4 plus variance of x5, and these, what we are assuming that all these random variables are independent, right? But the catch, let me recall you here one more time, that this is true when you have the fixed terms, right? So if you already know that you will have the two random variables here, x1 and x2, right? You already know that you will have the 5 random variables x and x2, but in this case what we are trying to find is that this is also a random variable n, so you will not have the prior knowledge that how many such n will be there, right? So in that case you cannot say that the variance of this random variable y will be the sum of the individual variance, right? Because this n is itself a random quantity, and depending upon the value of n, whatever it will take the value, right, that, so you will not have the prior knowledge that how many terms will be there within this summation, right? I hope you have a very clear idea what we are trying to find here. Alright, now here comes the picture that we have learned so far is the law of total variance, right? And this is what we have seen as the law of total variance. We are going to make use of this law of total variance to find the variance of this random variable y. Right? So again, to proceed further, what you will do, you will condition on this random variable n, and you will proceed further to find the variance of this y. So we are going to make use of this law of total variance. So let's first of all look at the quantities that we need to find. Here we have already the info about this expectation, that is the expectation of this random variable y given n, right? And what is this? So this is a random variable, right? And this we have seen that it is equal to n times the here, right? Now if we try to find the variance of this random variable, so this is the random variable, right? Depending upon the value of n, you will have it will take some value, right? Like here we have seen if n takes the value little n, we will have this value. If n takes some other value, we will have some another value. So we are seeing this as complete a random variable, right? And this is equal to this, right? So if we try to find the variance of this random variable, that is the variance of this random variable, that is equal to the variance of n times the expected value of x, right? And this is a constant, numeric value, right? The expectation of random variable x will be a constant. So we have already seen if variance of a times x is nothing but a square times variance of this random variable x, right? So we have seen in the properties, so that would be equal to, so this is a constant, so constant chi square times the variance of this random variable n. Alright, now coming to another term that we need to find is this, right? So let's first try to look at this quantity, that is the variance of y given n. This will be again a random variable. Depending upon the value of n, you will have, so if n is equals to n, if n takes the value little n, you will have some value of this quantity, and depending upon the n, you will have the variance. So overall what I am saying, that you can consider this as a random variable, right? Now if we try to find, so this you are able to see it as random variable, right? Let me describe. So if I say that this n takes the value is equals to little n, right? Then this quantity can be written as variance of, so y is the sum x1 x2, and this sum will go, given we have this information that n has taken the value little n, so the sum will go till this xn, right? And since these two random variables are this n and this xi are independent, so having this information will have no effect on my belief. So this conditional variance will be equal to the unconditional variance. And let's also assume we are assuming that since these have been taken from the identical distribution, and let's assume that each have the variance, that is variance of x. So we have such n terms, and all these are independent. So now this is fixed. So this till n we have the info, right? So these are the fixed. So x1 x2 plus x3 plus, and how many terms will be there till xn, because we have given this info, right? And all these are independent, so we can write this as n times the variance of this random variable x. What is this variance of this random variable x? Is the variance of each distribution, right? And we have such n terms of distribution, and these are independent random variables, so we can directly write that it will be n times the variance of this random variable x. So when we take n is equals to n, then this random variable takes the value this, right? So we can have a random variable, that is this random variable, and it takes this value when n is equals to n, and it will take another value when n is equals to n2. So overall this is a random variable, right? And we are trying to find this quantity, right? So if we try to find the expectation of this random variable, then this can be written as expectation, and this random variable is equal to this quantity, that is n times. So let me write here, so n times the expectation of x, sorry, the variance of x, right? And it takes, so let me repeat one more time, that it takes the value, so this is random variable, right? And this is equals to this, and this random variable takes the value n is equals to little n. So this random variable takes this value whenever n is equals to little n, right? And depending upon the value, it will have different value. And overall, what we are saying, that this is a random variable, and we are trying to find the expectation of that. This can be written as n times the variance of this random variable x, right? And this variance of this random variable x will be a constant quantity, so we can pull out from the expectation. So the variance of x, variance of this random variable x, times the expected value of this random variable n, right? So we have found this term and this term. Now we can write the variance of this random variable y, that is equal to sum of these terms, that is the expectation of n times the variance of this random variable x plus this term, that is this one, that is equals to the expectation ka whole square times the variance of this random variable n, right? So using the law of total variance, we are able to find the variance of this random variable y, right? So in case of the expectation, it was quite intuitive, right? So that if you have defined a random variable n, that is the number of store that you visit, and each store you spend the amount xi, and this is again a random variable that is identically distributed, and each one of are independent of each other, and this random variable and these xi are independent. Then in case of the expectation, it was quite intuitive that the total amount that you spend the expected amount that you spend is the product of the expected amount that you spend on each store times the expected amount of store that you visit, right? But it was not quite straightforward in case of the variance, right? In case of the variance, if you see the variance as a measure of randomness, so this randomness, source of the randomness is involved within this random variable x and within this random variable n as well, right? So if you would have considered this n as a fixed number, that you would have the early knowledge that how many terms are there in this summation, right? Then this n would be simply a number, right? In that case, the variance of that would be 0, so this term will be gone, and here you will have simply the expectation of this n is seems fixed number, so n times the variance of x, and we have already seen that if x1, x2, x3 are independent, and if you are trying to find the variance of that, that would be n times the variance of this random variable x, right? So the point is here, the if you see as variance as a measure of randomness, then this randomness contribution is from these two random variables, from these xi's, and since each xi has the variance x, so overall I can say that the contribution of the randomness or the source of the randomness is from this random variable as well as from this random variable. That is why we have seen this term as well. Alright, so see the power of this law of total variance, because using this we would have, or we are able to find the, using the total law of total variance, we are able to find the variance of this random variable y. Let's look at few of the properties of the conditional expectation. We have already seen this conditional expectation as a random variable. Now the very first property says that this conditional expectation or this random variable is same as this random variable. Let me tell you one point here, or one information, that I will be not going through the derivation of this property. It is quite intuitive property, right? And it will be true for discrete as well as continuous case. The proof of these properties, that I will not go into the details of that, right? But we can directly remember these properties. So let me first of all tell you that we are saying that these two random variables are equal, right? So if this random variable y takes the value y is equal to little y, then you will have the information about this function. So this function will give you some constant value, right? Depending upon the value, that depending upon the information of this y, this will be some constant, right? So easily we can pull out from this expectation, right? So depending or the based on the information of y, this function, that g of y, will be a constant. So we can pull out from this expectation, and this will be equal to this. So these two random variables are same random variables. And why we are saying these are random variable? Because we have already seen that the conditional expectations we can treat as a, or those are itself a random variable. Coming to the second property, what we are saying, that these two random variables are same or equal, right? So if this function h of y is a invertible function, right? So if you know the y, right, and if we have this function h of y, so if you know the y, you know h of y, right? So the value corresponding to this y will give you h of y, right? If h of y is invertible function, then what I can say, that if you know h of y, then you know for what argument of y you have got this, right? So if so, overall you got my point, right? So what we are trying to say, if you have the information about this y, it is same as having the information of h of y. Here y will take some argument, and that will correspond to some values of h of y. Or in other way, if you know h of y, and so you will be knowing that for what argument of y you have this h of y, right? So these two are the same random variable, right? That is all in this video. So we have almost seen everything about the conditional expectation. Now in next video we will be looking at a new chapter, that is the central limit theorem. That is all in this video. Thank you so much.